I am always insecure about this microphone not working. What are the degrees of substitution present on the carbons here? No one?
We're afraid.
They're all what? Okay. Nate, give me one of them. What's secondary? 2-degree carbon. Good. How many other secondary carbons are there? Good. The carbons next to it. And then some may argue that these carbons of the alkene are secondary because they are bonded to 2 other carbons. Some may argue that they are tertiary because they have 3 bonds to other carbons. I don't like to describe alkene carbons by primary, secondary, tertiary, quaternary for that exact reason. It's not clear. If I had to choose, I would go by the number of carbons it's bonded to and not how many bonds to carbon it has, because we've seen a lot of alkene addition reactions where a pi bond leaves and it creates a positive charge on that carbon, and it's not like calling this tertiary makes a tertiary carbocation. Calling this tertiary makes a secondary carbocation. So it's not easy. I generally don't ask you to do it, and I don't do it myself. How about this? Primary. Is it a methyl substituted carbon? No. Methyl carbons aren't bonded to any other carbons. This is a methyl group, but it's not a methyl carbon. Isn't that great? Primary. And this one? Tertiary. Good. This is a di-substituted alkene. In terms of alkenes, we have ethylene, which is non-substituted. Beyond that, we start to get mono-substituted. The di-substituted compounds come in 3 flavors. Di-substituted alkenes. I like to call this one terminal. I decided I liked that yesterday, because those of you that had me for OCHEM 1 know that I never called it terminal, but I have decided that is the best name for it. It's a terminal di-substituted alkene. You can see that the other 2 are internal di-substituted because the carbon chains, and those are carbon chain Rs, not any functional group R. You can't put chlorine there and call it mono-substituted. You can't put 2 bromines there and call it di-substituted. This is us describing bonds to carbon, much like we did here, right? The terminal di-substituted ends the carbon chain. That's a good descriptor. It's di-substituted and it's terminal. The internal di-substituteds can be trans, which we can also call E, or they can be cis, which we call Z. Then we have tri-substituted and tetra-substituted alkenes. I ran out of space. I wanted this to be a 1 list. Can you tell me what changes as you move down this list? More substituted, more R groups. What else? I'm looking for you to identify a trend here. With increasing substitution of the alkene comes, one more time? Increase in stability. Ethylene is what we would say is the least stable. In other words, the easiest to react with, which is why ethylene is a great starting material in a lot of syntheses. And tetrasubstituted is the most stable. We can think of this as the hardest to react with. We can also think of it as the easiest to form. when a reaction has the potential of forming different alkenes with different substitutions, it prefers to form the most stable, the most substituted. Okay, one last side question. How many degrees of unsaturation in this compound? 14. Okay, tell me what you meant by 14. I don't think there are even 14 hydrogens. 2, 4, 6, 9, 10, 12. Okay. Tell me why 1. 1 double bond. Tell me why 2. Ring and pi bond. Degrees of unsaturation come from rings and pi bonds. This compound has both a ring and a pi bond. So it is unsaturated twofold. And unsaturated is telling us what about a compound? That it could have more atoms. It could be saturated with more groups. But instead, some of these groups bond back into each other, limiting how many other atoms there can be. Okay, unsaturation does not always tell us reactivity. Rings don't necessarily have to be reactive. But pi bonds, things that we can generally react with because of MO theory. All right, let's talk about reactions, shall we? We have a number of different reactions. I want you to be familiar with their starting materials, products, and reagents. But another number of chemicals, a smaller number of reactions that I would like you to be familiar with their mechanisms. I understand that not all of you who came through other classes necessarily learned mechanisms the way that I'm expecting you to have learned them. So we're going to go over those mechanisms and make sure that we're all on the same page. Elliot, you got the one with reactions on it? Great. Those of you that took my OChem class, we're going to go through these basically backwards from how we learned them. We're going to start with that video is tripping me out. I'm watching myself talking to you. We're gonna go through these basically backwards from how we did it before. Let's start with reactions with alcohols. The molecule that I've given you, is it chiral or achiral? Chiral, which means I'm helping you identify features of this compound that, or of these reactions that influence chirality. So a bit of a reminder. One thing that we learned how to do with alcohols is elimination. We use H2SO4. This may sometimes be simply written as H3O+. This is considered an E1 elimination. Can you tell me what that means about the reaction mechanism? 2 steps, at least. Anything else? Carbocation intermediate. Carbocation intermediates will go for the most stable alkene. So that means more substituted, but it also means trans over cis. So there are a number of possible eliminations. The major product here is trans 2-butene. That's our only elimination pathway. We can also transform alcohols. This transformation is basically a substitution for the alcohol itself, but it's not actually substituting anything on the carbon. we will use a tosylate like tosyl chloride. If you're interested in the structure of tosyl chloride, stop it. Here is what its structure looks like, which is why I don't ask you to draw it out. This is TS. This is Cl. The process of this reaction takes OH and TSCl and leaves you with OTS. Is there a byproduct there? HCl. What about the byproduct of our elimination? Water, dehydration. What do you notice about the stereochemistry at the chiral carbon? Stays the same because that bond to O doesn't change. There are other ways that we can actually substitute our alcohol. One way is by using thionyl chloride or PBr3, tribromophosphide, or monophosphorus tribromide. Depending on which halide you want to get, but notice how the usefulness of this reaction gives you inversion of chirality. That's its benefit. I'm not going to worry about byproducts because they're just not as helpful in this case. The other way that we can substitute is by using HCl or HBr. What do you notice about the chirality here? Well, it's still a chiral carbon.
But I'm thinking like stereochemistry.
There's no stereochemistry shown. So has the chirality been preserved or eliminated? Eliminated. We now have a racemic mixture. That is 50-50 of both the wedge and the dashed configurations. If we were to label these, this orange one is technically an SN2 reaction because it's giving us inversion of that chiral center. And up above, we see an SN1. With alcohols, we can do SN1, SN2, E1, but not E2. If you wanted to do E2, you'd need to start thinking about multi-step synthesis. I can take my tosylate group, which now behaves more like an alkyl halide. And with the tosylate, I could introduce tert butoxide. I represent that as TBuO-. It just looks like this. I don't know why I screwed that up so bad. I'm pointing out tert butoxide because of its regioselectivity. I can already make this more substituted alkene just by doing E1. If I wanted to make a less substituted alkene, then I would need E2. How are you feeling about that reaction map that you've got? Is it too cluttered? Does it give you enough space to leave notes and leave information? You may need to kind of revamp it on your own and rework it to have your own cheat sheet of reactions. All right, let's do the next. Chiral or achiral alkyl halide. Chiral. What alkyl halide do I have here? None. None, because we could see chlorine, bromine, or iodine. To be fair, this is most often chlorine or bromine.
OChem one videos, do you
Yeah, you know what? I taught SN1, SN2, E1, and E2 in like one day in the fall and the summer. So you could find my OCHEM 1 videos from the fall and summer and see this reviewed in like one day. There's basically 4 things that we can do with alkyl halides. We can react them with strong base, strong nucleophiles, weak base, weak nucleophiles, strong base, weak nucleophiles, and weak base, weak nucleophiles. I think I did something wrong in there. 4 combinations of base and nucleophilic strength. So first, I want to look at strong base, strong nucleophile. That is something that's good at substituting and something that's good at doing elimination. This is something like hydroxide, alkoxides, and the acetylide ions, deprotonated alkynes. They're great nucleophiles. They love to share their electrons to substitute. They are also great bases. They like to go in and take a hydrogen. We can use stereo control. For the most part, you're going to know based on how the question is worded whether you're looking for elimination or substitution. But at a secondary carbon, these can do both. Elimination to give the more substituted, more stable, or substitution. Now I'm going to show OH, but this could be OR, or this could be a bond to the alkyne. Are you guys okay with that summary? With the way it's detailed? If you're not okay with it, then you can draw it 3 times. What do you notice about the chirality? It inverts. So is this SN1 or SN2? SN2, great. If we work with a strong nucleophile but a weak base, so this is weak base, strong nucleophile. This is something like sulfides, cyanides, azides. Those are the most common. Then we do not predict elimination. And again, we see substitution, inverting the stereochemistry, telling us that this is SN2. I'm sorry, I didn't say this well. In blue, we've got SN2 and E2. It has a mixture. It can do both. You know, sometimes students approach me and they say, I don't understand how a reaction can do both. Don't forget that you've got millions of billions of molecules. Imagine if you had millions of billions of days. Some days you would watch a movie. Other days you would build a fort. Those are very different things. And if you had millions of billions of days, things are going to control how you decide which one to do. Here it's all statistics of how the chemicals run into each other. And they have the possibility of doing both. Here, they really don't have that possibility. The dynamics, the energy dynamics, just don't support it. All right. We can do reactions with, let's go to weak base, weak nucleophile. I'm sorry, I think sometimes I call this weak base poor nucleophile. It's the same. You guys okay with that? Something that is not good at being a base and not good at being a nucleophile, this is something like water or alcohol. And the product that we get is either an alcohol or an ether or the most substituted alkene. What happened to the stereochemistry? It went away. Racemic mixture now. I don't have inversion. I have a 50-50 mixture. SN1 or SN2? SN1. Carbocation intermediate, removes the chirality. Can we predict then whether the elimination is E1 or E2? Good. If the reaction proceeds by SN1, if substitution proceeds by a carbocation intermediate, then elimination will also proceed by a carbocation intermediate. So this is also E1. Lastly, we can have a reaction with a strong base but a weak nucleophile or a poor nucleophile. Something that wants to take a hydrogen but is not good at getting in there and physically fighting against the groups at that carbon to make a bond. It's bad at being a nucleophile, but it's good at abstracting a hydrogen. Because these reagents are so big and bulky, they bring a lot of steric strain, they prefer to go to the less substituted position. This is tert butoxide and a chemical that we will learn later called LDA. We're not going to get into it right now. E1 or E2? E2. The carbocation intermediate will always prefer the more stable alkene product. So E1 always gives more stable. The only way to get this less stable product is by E2 with a base that is big and bulky. You guys know what bulky means? What do you use bulky to describe? It's been so long since I've used bulky to describe anything other than bases. A football player.
My dog is super muscular.
Yeah, like pit bulls are bulky.
Yeah.
So you know what that means then. You can't get your pit bull to fit through that doggy door because there's too much steric strain. You can't get your tert butoxide to substitute because it just can't fit into that tight spatial region. Never given that analogy before. What do you think about reviewing alkyl halide reactions? Questions? Do you want to pause now for mechanisms or come back after we've done all the reactions? Deal. I think that's for the best. There are some terms, dead men's names that we use. Zaitsev to describe the more substituted alkene, and anti-Zaitsev or Hoffman to describe the less substituted.
Oh, yeah, I was thinking. I was like, can you spell those again?
Yep, Zaitsev. Since Zaitsev already has one, I'm gonna name this one after Hoffman. It is truly a toss-up between chemists, whether they will call it anti-Zaitsev or Hoffman. I've seen Hoffman described as being selective types of anti-Zaitsev eliminations, but if you can remember anti-Zaitsev, now you also know that it can be called Hoffman. All right. Let's talk about reactions with alkynes. This one you can see is set up with a little bit more clutter, so you'll want to be careful how you organize your space here. Is it clear to you guys how the reaction arrows relate to the different starting materials? There's no confusion about which reactions are going to which starting materials? Why am I giving you two different alkynes? What's the difference between these? One's got carbon groups on both ends of the alkyne, internal. One's got only one carbon group and one hydrogen group, terminal. Kind of like we described our terminal disubstituted alkene, and internal. This is highlighting for us differences in regiochemistry. All right, one thing that we are going to highlight here is the ability for some of these reactions to do one equivalence with the pi bond versus two equivalences with both pi bonds. I want to take just a second to remind you, because we're flying. Did you see we're only half an hour in? Oof, I was worried we'd be like so far behind today. I want to take a minute to remind you about the learning objectives that are posted at the top of this module on RealChem. Great. So if you're worried about how you're going to keep track of all of these reactions and their names, they are listed here in this long list that is only going to get longer as the semester goes. You should look at Unit 5. It's like 6 pages. But there's a lot of repeat. There's a lot of like overlap. Okay, and you know what I do throughout the semester? I label them in your learning objectives as previously learned, so I repeat a lot, and new to this section, so that you can highlight what is new every time I write it and what is being repeated every time I write it. Is that fair? It gets to be a lot, doesn't it? Imagine I used to not provide these. Okay. With my terminal alkyne, I want to show you HX addition, one equivalence. That means across the two pi bonds, I'm only going to consume one pi bond. This we call a Markovnikov addition. This is a regio term. It says, stupidly,
I remember this topic.
the hydrogen adds to the carbon with more hydrogen. Why is that stupid? Because it has nothing to do with the hydrogen, and it has everything to do with the carbocation intermediate. We look to form the most stable carbocation. So let's just take a second to refresh on carbocations. Where would be the most, I'm going to add one more line. Where would be the most stable place to put a carbocation in this molecule? Did you say chair conformation? Tertiary, which is a much better answer, thank you. So primary, least substituted. I like to say that that positive charge on the carbon gets moral support from surrounding electron groups. This only has two hydrogens next to it, if there's a positive charge there, and one carbon group. Not a lot of moral support. Not stable. Secondary, two carbon groups, more moral support, more stable. Tertiary, the most moral support you can get. That positive charge is shrouded by electron density, so it's hard for anything to get at the positive charge, which means the positive charge is more stable. Allylic is in resonance, which means it's not a positive charge on one carbon, it's a half positive charge on two carbons. So I won't go primary, secondary, or tertiary. Degrees of substitution only goes up until you reach resonance. There are two allylic positions, secondary allylic and primary allylic. Which is the better allylic position? The more substituted with the more resonance. This is where the most stable positive charge can be placed, not here. So we rank first stability by degrees of substitution. Then we consider resonance plus degrees of substitution. Something with no resonance is always less stable than anything with some resonance. Primary carbocation, bad. Primary allylic carbocation, great. Isn't that wild? Primary allylic carbocation, better than tertiary. All right, I do want to pop over to the other side now, and I want to show you HX in two equivalences. Now, I do this on the internal one to show you a second feature of the regiochemistry. I think you'd all believe me that if I did two equivalences to the terminal carbon, the halogen would go to the same position twice. It's Markovnikov twice. This does not have Markovnikov or anti-Markovnikov. Neither of the carbons have hydrogens. So after you have one equivalence of HX, how do you know what happens to the second equivalence? Does the halogen go to the same position as the first time, or does the halogen go to a new position? And the answer is the halogens will always go to the same position, which means we can describe the regiochemistry of the two equivalence addition as geminal. Who are my Geminis again? Oh, just me? Do you guys know why we call it geminal? It's not two-faced, but it's twins. The reason Geminis are called two-faced is because the Gemini is the twin star sign. So it's almost like you've got two versions of yourself, two faces you put forward.
I don't think I've heard two-faced, but I've heard crazy.
So geminal, because those halogens are on the same position. All right, I'm going to keep going in this clockwise direction, and we're going to look at hydrogenation with palladium and charcoal, palladium on carbon. How many of you did this last semester in the OCHEM 1 labs? Good number of you. It was just that black powder, right? Did you do over the summer?
Yeah.
We had that big contraption. We were bubbling stuff into it, and it said, don't add the palladium too fast or you'll catch the methanol on fire. Fun stuff. Okay, in this reaction, both equivalences of the alkyne pi bond are reactive to hydrogenation, and so we get a fully reduced. Reduction here is just adding things that are less electronegative than carbon. Fully reduced alkane. Are you okay with the fact that this requires two equivalences of hydrogen, but we're not going to say two equivalences? Because there is no way to add this reaction stoichiometrically. You always have to have an excess of that hydrogen gas to push this reaction forward. So it is excess, it is two equivalences, we just don't say it, we assume it. If you're not okay with that assumption, write it on there. The other way that we can take an alkyne and reduce it is by using hydrogen gas in combination with a different catalyst, Lindlar's catalyst. I TA'd for a professor who took off points if you spelt Lindlar's wrong, which is so funny because that guy doesn't care. He's not rolling over in his grave. The reason that I use Lindlar's catalyst instead of the actual chemicals is that the chemical list is much longer. It involves palladium and carbon, but it also involves a barium carbonate salt and quinoline, and it actually acts as a poison. This will form a cis-alkene. The cis-alkene also forms in total hydrogenation. It's the first equivalence of hydrogenation, and then that alkene gets hydrogenated as well. Lindlar's catalyst is to make the alkene inert to the hydrogenation. So it poisons the reactivity of the alkene. The last one here is if I take sodium and ammonia. You may also see this written sometimes as lithium and ammonia. I do want to point out that this is not NaNH2. That is a salt. This is two different chemicals. Metallic sodium with one valence electron, a reducing agent, and ammonia, a source of hydrogen. This will give us a transalkene. Those of you that took my OCHEM 1 class or want to go back and watch the video know that I love the mechanism of this because it uses electron repulsion to predict why the groups are positioned trans rather than cis. It's great. We're not going to go through the mechanism. Yeah?
You said that the one with the palladium was two equivalent, or assumed two.
That's right. It's assumed two equivalences.
And the one with the Lindner's catalyst, is that considered cis, right?
This is a cis alkene. Good. And this is a trans alkene. So you can see the value of both partial reductions. One partial reduction gives you a cis conformation. One partial reduction gives you a trans conformation. So if you need specific stereochemistry, you can control it. All right. Some of our other ones. Hydration. Our first hydration for the alkyne uses mercury sulfate and sulfuric acid, HgSO4, H2SO4. This is a combination of the alkene addition reactions, acid catalyzed hydration, and oxymercuration put into one. This is Markovnikov because of that. It gives an intermediate that you do not isolate. So I'm not going to show you the intermediate. I'm going to show you the product that you isolate. You isolate a ketone. If you're interested in the intermediate, okay, fine. It's an enol. It's a more substituted enol. Our second hydration is two steps. First, borane. Second, basic aqueous hydrogen peroxide. Hydrogen peroxide dissolved in water with an elevated pH. This will deprotonate the peroxide and makes it more reactive. The water acts as a solvent to allow this to happen. Basic aqueous hydrogen peroxide. Hydroboration, first step. Oxidation, second step. This gives also an enol intermediate, but it will give us a less substituted enol and a less substituted carbonyl. Aldehyde versus ketone. Questions?
Step two, like all of those? Or?
Yes. You add a solution.
Yeah.
You know how you could add like water or you could add basic water? And in the same way, you could add water with, I'm trying to think of something else you might think of, like water with bleach or basic water with bleach. So this is adding hydrogen peroxide dissolved in water with an elevated pH. So it's basic aqueous hydrogen peroxide. The most important chemical there is the hydrogen peroxide. But in order for it to be reactive the way that we want it, we need it to be basic. So really the two most important are sodium hydroxide and hydrogen peroxide. All right, one last reaction here. Let's look at, I'm going to kind of run out of space, to be honest. So I think I want to show you guys ozonolysis. There are two ways that we'll do this. O3 with H2O2 or KMNO4. These will do the same thing, oxidative cleavage. What that cleavage means is cutting the carbon-carbon triple bond in half and creating two separate carbon groups. One carbon group on the left becomes a carboxylic acid. And one carbon group on the right, in this case, becomes carbonic acid, which actually decomposes just like it does in your water, or sorry, in your sodas, it decomposes into carbon dioxide and water. If you didn't do this with a terminal alkyne, if you did this on an internal alkyne, you get 2 carboxylic acid groups. But this is more interesting to show on terminal because the 1 carbon at the end gets turned into a dicarboxylic acid, which then decomposes and is basically just waste. Okay, other questions? Do you want to take a picture of this before I erase it? Yeah. Good. Anybody else?
What's the erase part?
Substitution of carbocations. All right. You can see that we've got a few more reactions with alkynes to go through. So to the right, I want to show you, and we're going back to this terminal alkyne because it has a few more things to do for us. First, let's look at halogenation, X2, 1 equivalence. Always, always, the product will be trans. Those halogen groups add opposite to each other. To be honest, I'm not happy with the way that's drawn. We describe these two not as geminal, but as vicinal. They're on adjacent carbons. They're in the same vicinity, but they're not on the same carbon, so we call them vicinal. But these halogens also have another descriptor. They're also called vinyl because they are attached to an alkene. Vicinal and vinyl, they both describe these hydrogens, but I don't want you guys to confuse them. They're similar, aren't they? Vicinal and vinyl. But they are describing distinct properties of the halogens. All right. Right. Halogenation, 2 equivalences, or in excess. I refer to this product as a tetrahalo product. You get 4 halogens. You really don't see it used that often. I don't see it used that often. Now, we have talked about adding H and X, Markovnikov, but there is also a way to add them anti-Markovnikov. So these first 2 ways that we added HX, always added to the more substituted carbon. Let's show a way to add them to the less substituted carbon. This is HX with peroxide, 1 equivalence. The only difference is that the halogen is now less substituted, and the hydrogen has added more substituted. We call this anti-Markovnikov. Markovnikov didn't know what he was talking about, so this is like named in his honor. I think it's offensive. I offend him with it. No. Anyways, do you know what ROOR is? Peroxides. So a good example of a peroxide that you could use here, hydrogen peroxide, H2O2. You could write this as HCl, H2O2, HBr, CH3OOCH3. That would be methyl peroxide. There's a lot of options. HX with peroxide, 2 equivalences, gives us our anti-Markovnikov dihalogen product. Is this a geminal product or vicinal product? Geminal. Great. What's the only thing that we have not shown done with our terminal alkyne? Epoxide? We won't epoxidate an alkyne. We will with the alkenes. Addition of substitution. So actually, it's not addition, because addition is taking a pi bond and adding two new groups where that pi bond was. This is alkylation, where we will add an alkyl group to the carbon. It's technically a type of substitution reaction, and earlier we showed it. Terminal alkyne that has been deprotonated, acting as a nucleophile, and I can see now why it really doesn't make sense not to show it. Acting as a nucleophile and forming that bond, but that looks weird at the same time. It's still not pretty. Oh, that's why I can't do a zigzag. SP geometry, linear geometry, SP hybridization. Okay. I don't have an ion right now. So how do I make this to be an acetylide ion? Deprotonate it. And in order to deprotonate it, I need something basic enough to deprotonate it. We saw our pKa table last week. We said alkynes are more acidic than deprotonated amines, deprotonated hydrogen, H2, and deprotonated alkenes and alkynes. So one of the most common ways to do this is first introduce sodium hydride or sodium amide. Remember I told you sodium amide is a salt, and I don't want you to confuse it with sodium and ammonia. Sodium amide, sodium hydride, great bases for deprotonating this alkyne. Then we introduce an electrophile, and we do substitution. How big do you want this electrophile to be? What group do you want to have attached to it? Those are all questions that you can decide. But remember, since the acetylide ion is a strong base, strong nucleophile, anything that is secondary substituted or more is going to have trouble with elimination. So acetylide works best on primary carbons. You're going to see it mostly with primary carbons. So let's give an example of a primary carbon electrophile. I'll have a halogen, I'll have a primary carbon, and then I'm just going to show this as R. But the primary carbon is this CH2 group. Here's my product. If you're having trouble predicting how long to make your carbon chain, if you're having trouble knowing where to make the bonds, then I recommend mapping your carbons, which is not quite the same as just counting them, but it uses good logic to predict where bonds are going to form. I like to count through my nucleophilic carbon to the electrophilic carbon. You guys remember these terms? What is a nucleophile? Sarah? It's okay? Yes. No. Nucleophile? Likes nuclei. Nucleus loving. Meaning, how is that reagent going to get to another nucleus? It's going to have to share electrons. Electrophile? Electron lover. So, so it accepts electrons. So nucleophile in this case will be my acetylide ion because it's going to have that negative charge. After this first step, I end up getting this negatively charged acetylide. That's my nucleophile. So I'm going to count through it. 1, 2, 3, 4. Carbon 4 is my nucleophile. What's my electrophilic position? The halogen, the CH2, or the R group? Where's my electrophilic position? Where should number 5 come in? Halogen, CH2, or R? CH2 gets attacked. R gets kicked off. So I'm going to ignore, I'm sorry, not R. X gets kicked off. I'm going to ignore X. 4 attacks 5. 5 is attached to 6. Now I can go back to my product. 1, 2, 3. 4 attacks 5. 5 is connected to 6. Where is the X? Gone. It's been substituted. The halogen was substituted for the alkyne. Questions on the alkyne reactions? How many of those are new to you guys? Especially those that didn't have me in OChem 1. Any? A lot? Did you take it up at the U, you said? Weber. And sometimes different schools will actually teach them in alkynes in OChem 2. The nice thing is, it's pretty similar to the alkene reactions, just a lot of them are doubled. So let's do the alkenes. Shall we? No. First, alkane. I want to do the alkane first because it's very simple and because it's at the top of your sheet.
That's what you had in the finals, oxy, that's stuck in my brain.
All right, so I've got this alkene for you. No, I don't. I've got this alkane for you, and this alkane has primary, secondary, and tertiary carbons. So the full range of substitution, yeah? There's only one thing that I can do with this. Okay, there are two. I can burn it, and I can use the energy that comes out of combustion to drive my car. We're not going to talk about that. And to be fair, I don't know the mechanism for the combustion. I wish I did. I've looked it up. It's hard to find a good answer. The arrow pushing is just like not very clear. What I do know is that it happens very quickly, because when you think about an 8-carbon chain like octane, losing all of its CH bonds for OH and CO bonds, that's crazy. And it happens in an instant inside of your piston. Okay, there's only one thing we'll do with this. There's only one thing synthetically useful for us, and that's bromination. Br2. What does H nu tell us? Light. Heat is delta, the triangle. Why do we represent H nu for light? I guess it's cool. It's like, is it harder to just write L-I-G-H-T? And specifically, this is usually UV light. Now, one of my OChem 1 students from the fall messaged me and said, I found this document, and it says bromination requires light and heat. Somebody else messaged me, an OChem 2 student of mine from the fall, and said, I'm studying for the dental exam, and this document goes through, and it only says heat, and it doesn't say light. They're not the same thing. Light and heat are different. Light can be a form of heat, but heat can also be just kinetic motion.
Is that one of the tests we offer at SLIC?
It depends on who you take.
Someone needs to slap that person.
To be fair, they can be used interchangeably. It may depend on what conditions you're using. So I just want you to be familiar with this because that is what I'm going to use. Some of you may have also seen that you can substitute Br2 with NBS You won't see this just yet. We will talk about it in our next chapter after the unit test. We'll talk about the applications when NBS is useful. Okay. Also, I do want to point out, I have been pretty consistent about not telling you which halogen to use because you're able to use different halogens. I'm being specific now. This is not a halogen you can swap out. Chlorine is too reactive. It goes everywhere uncontrollably. Bromine is selective enough in its reactivity that it always gives us this most substituted product. I'm sorry, that was a weird R. Is BO an element? I don't think it is, but I don't know most of those intertransition metals well. Okay, that's it. You got a halogen? Brominate it. If you're going to brominate it, where does it go? Most substituted, always. Why? Because Markovnikov told you so. No, because of the carbocation, but it's not a carbocation. It's a radical. And the radical intermediate has the exact same stability trends as carbocation intermediates. Stability increases with degrees of substitution, and then stability starts over with increasing degrees of substitution and resonance. Anything allylic, always more substituted, more stable than anything without resonance. All right, now the alkenes. And you can see we've got the most to do about the alkenes. Well, I guess the alkynes had a lot. First, I don't want this. Let's do HX addition. HX, HCl or HBr. Markovnikov, because of the carbocation. So the carbocation forms on this more substituted position. And that secondary carbocation is adjacent to a tertiary position. The tertiary position would be more stable with the carbocation. So it goes through a hydride shift. It gives a carbocation rearrangement. Hydrogen moves over. A new carbocation is formed in its wake. And this is what reacts.
When you're saying substituted, would it be wrong, like my brain when I go, oh, it has less or more hydrogens?
Okay, well, you got to pick whether it's less or more hydrogens. So if I say the carbocation forms on the more substituted carbon.
So I think less hydrogen.
Less hydrogens.
Okay.
Because that is what, in theory, we're substituting. You're taking away a hydrogen from that carbon to replace it with a bond to carbon instead. More substituted hydrogens for carbons. So add the carbocation to the carbon with less hydrogens.
Okay, so I'm okay to think like
That's
that.
perfect.
Okay.
HX with peroxide. Anti-Markovnikov, just like last time, which means my hydrogen does not add to the primary carbon. My halogen adds to the primary carbon. There are no radical rearrangements, thank God. So this is it. That's all we get. Let's do X2. I will admit that I show less information than some people here. Some people will give you a solvent. They will tell you that this is being run in THF, ether, dichloromethane. It doesn't matter. If the solvent is not listed, then the solvent is not interfering. This is a dihalogenation product, and it is anti-addition. The two carbons that form have opposite stereochemistry. Oh, do you guys want a break? Sorry. Let me get through this next one and I'll give you guys a break. I was just going to go. I was so happy about the pace I was on.
Just driving us to the ground.
Chiral carbon? Yes or no? Yes. Chiral carbon? Yes or no? No. So do I need to show the stereochemistry at this achiral carbon? No, I don't have to. Because this forms a chiral center, it will form a racemic mixture, both versions of that chirality form. And you can show that it's anti-addition even when the stereochemistry doesn't matter, but you don't have to show that it's anti-addition if the stereochemistry doesn't matter. So I'm showing it to you as a reminder, but if it's achiral, you don't have to show that stereochemistry. All right, if we run X2 in water or alcohol as our solvent, now the chemistry matters. The solvent interferes. If we run in water, we get a vicinal halohydrin. If we run in alcohol, we get a vicinal haloether. I do want to point out, whether it's water or alcohol as the solvent, the oxygen only loses a hydrogen. When alcohol loses a hydrogen, it becomes an ether. When water loses a hydrogen, it becomes an alcohol. Water precurses alcohol, alcohol precurses ether. I see this a lot where people show alcohols forming alcohols. That means you broke a CO bond, and that's not easy to do. What's much easier to do is break an OH bond and be left with an ether. All right, with that, I'm going to clear more board space. Let's take a 5-minute break and come in a little bit. Can't do that math. What's 5 minutes past 9? Oh, 14. 6:14. I usually just say somewhere between the two numbers.
It's late and we're all hungry.
Are you hungry?
Yeah.
Oh, because you just came out of lab.
Well, and I don't want to have to, I don't eat usually on days I have to come in, or like if I'm feeling well, because I just don't want to activate any.
Sure.
I literally don't eat for like a whole day.
Scary, because you also don't want to activate something by not eating, you know?
Can I ask you a question? Why does the presence of peroxide make it the less substituted?
Great. Why does the peroxide change the regiochemistry? So I think to answer this, what I'll show you is glimpses of the mechanisms of both. I've already shown you that when you have the alkene and HX, the intermediate you form is a carbocation. What this doesn't highlight well is that the hydrogen has added to the less substituted carbon. CH2 becomes CH3. When the alkene reacts with HX in peroxide, well, actually, the alkene doesn't react with HX in peroxide. First, the peroxide splits. It becomes two radicals. Then, one of those radicals abstracts a hydrogen. So you're really dealing with an alcohol and a halide radical. Now, that halide radical forms a bond to one carbon and breaks the pi bond into a new radical, propagates the radical. You know what propagate means here? one radical begets another radical. The radical propagates from one species to a new species. In biology, we use propagate to say like new life, yeah? If I propagate my plant, I start with 1, I could end up with 10. Here, if I propagate my radical, I start with 1, I end up with a different 1. It's a transfer of that radical. Halide radical bonds to one carbon using one of the pi electrons. Where does the other pi electron go? It goes to the more substituted carbon. Now, this reacts with HX, whereas here, this reacts with X minus after it actually goes through that rearrangement. This now reacts with HX, and so the hydrogen adds where the radical is.
That's interesting. How does it gain that energy to break into radicals initially?
Peroxides are not very stable. That OO bond, they're both electronegative atoms, so they both want the electrons. So heat or light can split that peroxide bond into two radicals. And radicals are not stable on their own anyways. So once that radical forms, it goes looking for other things that it can bond to become more stable. You're taking the labs or no?
Yes.
You also know that in a lot of these reactions, you're boiling this stuff. You're heating it up really hot. That's another way that you can provide that energy, right? How do I break the bond, but then how do I break this bond, and then how do I break that bond, and then how do I break this bond, and then you just have to constantly be putting in energy so that things stay at elevated energy levels. Ozzy, did you want to add something to that?
Oh, I was just saying, I remember you saying whenever a radical was made, we like expect that one will. I remember you saying.
There is another step. So initiation,
Yeah, that's
no radicals become two radicals. Propagation, one radical becomes another radical. And then termination, two radicals become no radicals. No.
I was like, very super fun.
It won't be a big component. RIP.
That's okay. I just was like, I kind of remember that. Anyway, I have like everything written down, so that's why I was like, okay, just tell me these. I'm just gonna go through them.
Good. Is it time? It's time. Oh, I didn't even get a break, did I?
Yeah, you did get a break. You hung out with us.
I don't need a break. That is a break for me. Sometimes I worry that there's such breadth of content that I don't want to get into too much depth as well. Because if I get into too much depth, I won't have the time to cover the breadth of it as well. So I love this explanation on the left. Why do they give us different regiochemistries? It's because of how they react. Peroxides produce radicals. Radicals interact with HX to create new radicals. Radicals react with alkenes to form new radicals. And acids like HX just react to form carbocations. So it is the mechanism. It's the meaning, the definition of why these things happen. But it also takes a long time to explain and show and understand and memorize.
But we like the detail.
Totally, totally. Okay. Are you ready?
If it's brushed over, I'm like, what?
Can I ask you a question about that one? Can that one do is it stereochemistry? Does that change?
Yeah.
Be like
So it's always
in a dash?
anti.
Yeah, but one of them could be a dash and one could be a wedge.
They could flip.
What is that? Is that when it's a racing mixture?
Yeah. Unless there's another chiral center somewhere else in the molecule that is not changing. And when these two change, but that other one doesn't, now it's a diastereomeric mixture. But here, both versions form, so it's a racemic mixture. Okay. Planar, achiral. Next, let's look at ways to add more water. So our first method will be acid catalyzed hydration. The product that we get here should remind you a lot of the product that we got from HX addition. Notice how the alcohol adds to a carbon that was not originally a part of the alkene. The alcohol adds to a carbon that used to have a hydrogen. Where did that hydrogen go? It shifted. The hydrogen shifted to create a more stable carbocation. This is a carbocation mechanism. We can avoid carbocations by first adding mercury acetate and water. That's OAC, the conjugate base of acetic acid. And following this with reduction. Sodium borohydride is a source of hydrogen. So this is oxymercuration reduction. This also gives a Markovnikov hydration, but it does so without the carbocation rearrangement. I should have done a different color. Another way that I can add water is by hydroboration oxidation. Once again, BH3 with basic aqueous hydrogen peroxide. This time adding the OH group to the less substituted carbon, adding the hydrogen to the more substituted carbon. Those three are all hydrations. So the last one is not technically a hydration, but it's similar. If we use osmate, that's OSO4, not O5O4. Osmium tetroxide gives a syn addition diol. You guys are okay if I clear this first set of alkene reactions?
Was this sheet on the page too when you printed out those?
Yes. Yep. Do you need one?
I have one, but I also want to do more now.
Totally.
Thank you.
Yes. Yes. All right. Getting to the end. Do I have one set of molecules that's different? Yes, I do. So we're on to that one, aren't we? Hydrogenation, H2, PDC, takes an alkene, reduces into an alkane. This is why Lindlar's catalyst is so important. Lindlar's catalyst will prevent hydrogenation from happening on the alkene. Otherwise, an alkyne gets reduced to an alkene, and the alkene gets reduced to an alkane. I want to show you ozonolysis, two forms. We can do reductive ozonolysis, ozone, with dimethyl sulfide or with zinc. It has to be zinc with ozone or dimethyl sulfide with ozone. This is referred to as reductive ozonolysis. Even though it's oxidizing the carbons, if there is a hydrogen present, it will not oxidize the hydrogen into an OH. This will compare to potassium permanganate or O3 with hydrogen peroxide, which does take that hydrogen, the vinylic alkene hydrogen, and oxidizes it into a carboxylic acid group. A more reduced product, a more oxidized product. And you can see it's more oxidized because there are more oxygens. Reductive ozonolysis, oxidative ozonolysis. I ran out of space. I don't have everything here, so we're gonna have to add one to your little table. Last one here will be epoxidation. That is MCPBA. And epoxidation adds Ozzy's favorite 3-membered ring.
We're all friends.
All right, so here's the one that I didn't show you. I think I'm going to go back to one of these mono-substituted instead of tri-substituted products. On this mono-substituted product, I do apologize for this. We're going to do the same thing we did to the alkane. We're going to add Br2 with light. At this point, we have seen Br2 alone, Br2 with alcohol or water, and now Br2 with light. So bromine does a lot of different things depending on the conditions that it's in. Bromine with light will not act as Br2, it will act as 2 bromine radicals. So the pi bond is not added across. Instead, the pi bond stays intact and we form an allylic carbon radical. There's only one allylic position here, which is why I didn't go up there, which has 2 distinct allylic positions. This allylic position, if it forms a radical, is a tertiary allylic position. But because it's allylic, it's in resonance with a primary allylic position. And these allylic systems can lead to 2 different structural isomers. I call them 1,3 allylic isomers. The first isomer looks like the alkene, but bromine has been added to the allylic position. And the second isomer has that 1,3 swap. Haley? Vinylic is attached to the alkene carbon. So this would be a vinylic position. If the radical was on that carbon, it would be a vinylic radical. This position attached off of the alkene is the allylic carbon. So the radical being on this position is allylic. 2 isomers. This will not be super heavily tested on this weekend, but I do want you to be aware of this idea. And this actually brings me back to MO theory, if you will. We now have a 3-atom system, each with p orbitals. If we consider the molecular orbital that comes from those 3 atoms with p orbitals, the lowest energy is when all 3 overlap in phase. And according to this allylic radical, we do have 2 pi electrons that will occupy that. This is telling us that there is a pi bond, not between any 2 positions, but a pi bond across 3 atoms. It's beautiful. Then, at the highest energy, I would see all 3 of these p orbitals out of phase with each other, a node separating them. This will be empty. If this were occupied, there would not be any pi bonding. Their pi bonds would all be broken. Notice how we've gone from 0 nodes, all in phase, to 2 nodes, all out of phase. That tells me that in the middle, there will be 1 node, And that node is going to lie symmetrical. That node is going to fall directly over that central position. These two orbitals will be out of phase. That central atom will not experience the presence of these electrons. And how many electrons there in my allylic radical system? 1. The radical sits here. It sits on positions 1 and 3. 1 and 3. This is what we refer to as movement of pi electrons. This is why we call it delocalization of pi electrons. That radical is not moving between positions 1 and 3. It's only at positions 1 and 3, and it's at both positions 1 and 3. It's beautiful. So how come carbon 2 never gets to make a bond to the bromine? Carbon 2 never has that radical reactive electron. There's a node over carbon 2. It doesn't experience the electrons. Are you comfortable with the idea that electrons move from 1 to 3, are at 1 and 3 at the same time without needing to go through the space that is atom 2? You're comfortable with it? Good. I'm glad to hear that. Because waves do that, and that's what this is representing. It's representing the electron wave. If this is my ocean, and I have a wave that does this, did I give you guys this analogy? We would say there is no wave here, and there is no wave here, because that is the baseline of the ocean. But the wave is different here from what it is here. So this is just where the wave is not existing. And the electron is on one side and the other, but not in the middle. MO theory to save the day, right at our 11th hour. Elliot.
In active products, do you need to move the alkene between carbons 2 and 3 and then minus 2?
Yes, I did. So this is what I refer to as 1,3 allylic isomers. The radical first forms at that allylic position. And so I can place the bromine there because that radical does exist there. But the pi bond is not just between atoms 2 and 3. The pi bond is now between atoms 1, 2, and 3, which means that this also exists as much as this does when the radical sits on this position. Here's that alkene, here's that radical. Remember that MO theory would say these don't exist. This exists. What the hell is that? Kind of looks like an eyeball ready to blink at you. That doesn't actually clarify that the radical is only at positions 1 or 3. That does a better job of describing MO's theory's prediction that there is a pi bond across all 3 atoms, but it doesn't clarify that MO theory predicts atoms 1 or 3 to be the radical. So 2 structural isomers where the pi bond moves from 2 to 3 to 1 to 2. Cool. I do want to make a quick note of the Diels-Alder reaction. I do not have it on your sheet. We are not going to see it much, but I don't want you to think that it's a meaningless reaction. So I'm going to give you a basic example. In Diels-Alder, we need a we call it an S-cis diene. And we react the S-cis diene with a dienophile. That dienophile typically has some electron withdrawing conjugated group. So I've shown it with a cyanide here. When you predict the products, I don't like the name Diels-Alder because it doesn't tell you what to expect. I like the name 4 plus 2 cycloaddition. You'll take these 4 atoms of the diene and these 2 atoms of the dienophile, and you'll use them to make a 6-membered ring. 4 bonds to 5, 1 bonds to 6. Of the 3 pi bonds in the beginning, this is not a mechanism you need to know, but I know some people benefit from seeing it. Only 1 pi bond will remain, and it will come between atoms 2 and 3. And then, of course, our electron withdrawing group also shows up as a CN. If you wanted to add more complexity to the dienophile, it's as easy as this. If your dienophile is cis, if there are 2 groups coming the same direction, then they will also be cis in your final product. If they are trans in the dienophile, they will be trans in the final product. If they are not cis or trans, because dienophiles can also be alkynes, if they are linear in the dienophile, then they will just be an alkene in the product. You only consume one of those pi bonds. Not something we'll work with often, but something I do want you to be familiar with. For those of you that are doing compounds that maybe have a ring and has a pi bond in it, you can look at doing a Diels-Alder reaction in your synthesis during your analysis assignment this semester. So I do want it to be on the table. Let's do mechanisms, shall we? I want to add a document. I didn't have time to print this off, I'm afraid. So I'm going to encourage you to just follow my notes. But I'm going to upload a file from my OChem 1 class from this last spring. I guess it's 2 files. I think I'm going to have to upload them later because I don't know if I can. I don't want to upload the wrong things right now. So I'll just project them for now. First, I think I want to go through substitution and elimination. Yep. Here are the mechanisms that I want you to be able to show. You have a written homework that I will give you feedback on your mechanisms on, and you will have to show mechanisms on the unit test, part B, the short answer. So these are the mechanisms I want you to know. That's why I'm having you do the written work, so that I can give you feedback on whether it's working or not. I want you to be able to show me SN1 or E1. These are similar to each other because of how they start. So here I have the steps needed. Both of these start with a leaving group leaving. That is, a carbocation forms. So I want to take a simpler structure with you guys. Tert butyl bromide. To show the leaving group leaving, how does a bond break? A bond breaks to the more electronegative atom. So carbon breaks its bond to bromine. This gives us Br minus and a carbocation. I'm going to show these stepwise. You can combine these steps and have a fully sequential mechanism. It's up to you what you think you understand better. Second, and actually I've got this written down, but I'm not going to give you one with this. There can be a carbocation rearrangement. None for us to show now. Second, a nucleophile attacks if it's SN1, or a beta hydrogen is removed if it's E1. So let's take this carbocation and let's show water acting as the nucleophile, and let's show water acting as the base. As the nucleophile, a bond forms between water and the carbon because of oxygen. Bonds form from the more electronegative atom. Those are oxygen's electrons to choose what to do with. As a base, I will need to highlight one of these hydrogens. In this case, it doesn't matter which, because they're all 9 identical to each other. But I need to take one of those hydrogens, and water will act as a base. Its lone pair bonds to the hydrogen. How many bonds can hydrogen have? Only one. So the CH bond needs to break. When a bond breaks, it goes to the more electronegative atom. Who's more electronegative, carbon or hydrogen? Carbon. What will carbon do with these electrons? Why does it want a lone pair? It doesn't. So it will share them with the carbocation adjacent to it. And this gives us our final product, an alkene, H3O plus, and Br minus. Elimination. E1 via carbocation intermediate.
And then will the BR attack H3O usually?
HBr is a very strong acid, so it's not easy to form. So H3O plus and Br minus are the most likely products.
So they'll be happy.
It'll be done, yep. Now, after this nucleophile attacks, what I get is oxygen with 3 bonds and a positive charge. So what we need here is a second step. We'll call it 2A. I simply need to deprotonate the nucleophile that attacked. Oh boy, what could possibly deprotonate? There are 2 plausible options. Br minus, which we already formed and has just been sitting around with nothing to do. And I'm sorry, I wanted to show that this has a reaction arrow forming down to this. So I could show Br minus, which is still around, still has nothing to do. I'm also doing this in water. Water is the solvent, so there are thousands of times as many water molecules as there are reactants. So I can show another water molecule. Either one can be shown. I'll accept either. I'm going to show water, deprotonating that water, breaking the OH bond back to O, and it gives me substitution. SN1 and E1. On your written homework, by the way, I fixed the written homework and I re-uploaded it. So I think a couple of you had downloaded it before I fixed it. I'll accept it. It's like basically the same, but I changed a couple of the problems to make it a little bit better. And I changed the points. So I will be grading it on the new points and not on the old points. You will get to pick between SN1 or E1 with the same number of steps because they're the same number of points. These do not have the same number of steps. So when you pick one, you will realize one will have a carbocation rearrangement, one will not. All right, SN2 and E2. I'm sorry, I should have shown this. I didn't give you the reaction. This was if tert-butyl bromide reacted with water to give tert-butanol or 2-methylpropene. That was the overall reaction that we just showed. With SN2 and E2, we're going to use a strong nucleophile and a strong base to show how these two work. One of them proceeds by a backside attack. The other proceeds by antiplanar elimination. These are both one-step mechanisms. Now, I know I didn't have any stereochemistry in that first structure, and that's because it's an achiral carbon. But to show antiplanar elimination, I need to show that the leaving group, bromine, and the beta hydrogen are anti to each other, one wedged, one dashed. SN2, 2 arrows. Hydroxide nucleophile attacks carbon electrophile, breaks off the carbon-bromine bond. Isopropanol and bromide formed. E2, hydroxide bonds to a beta hydrogen, CH bond breaks to form a CC pi bond, and bromine leaves. 3 arrows all at once. This leaves me with water and bromide byproducts. What's easier? SN1 and E1 or SN2 and E2? SN2, E2. I think so too. And maybe you don't agree with that, but I don't know why. If you don't, tell me why. I don't know why you would. But which one is going to be worth more points? SN1 and E1. Did I tell you guys how I assign points here? I told you on the new homework. Haha, see, I'm getting better at this sometimes. On the new homework assignment, I have gone through and told you that I assign points based on the number of steps in the mechanism. Half of the points are graded by the accuracy of the arrows. Do you have the right number? Are they pointed in the right direction? The other half of the points is graded by the structures. Are the bonds formed correctly? Are the bonds broken correctly? Do you have your charges shown appropriately? And stereochemistry. Is your stereochemistry appropriate? So I have changed the points since the semester started. I will be updating some of the other ones as we go too. Lily?
Wait, so that's how you grade our homework and our exams?
Correct. And the unit tests. So on a unit test, when you see a mechanism problem and you see the number of points, you know that that is somehow informed by the steps in the mechanism. And when you see the number of points, you know that half of those points come simply from drawing the structures correctly. You could draw the structures correctly without any arrows, and you would be halfway done with the mechanism. I think that's fair. If you know the structures and you're not sure about the arrows, you're halfway done. And then the other half of the points come from the arrows. So on the unit tests, it's usually not the number of points is equal to the number of steps, because that can be a lot of points. So it's informed by the number of steps. How did I phrase that on here? The number of points are based on the number of steps involved. Deal? No ambiguity. I don't want you to be nervous about how you're going to get graded. Structures and arrows. That's your mechanism. Elliot?
Are you okay with just showing bonds forming from like a chart, not a lone pair, like you did on the second one?
Yeah, so here's a good question. Why do I show this lone pair when oxygen has 2? This is what I refer to as a relevant lone pair. That lone pair is used to form a bond, and that atom has no charge for me to start from. I don't have to show the other lone pair because it's not being used to form a bond. I could show any of the 3 lone pairs on hydroxide, but I don't need to. The negative charge indicates an extra lone pair, so I can start from the negative charge. Good question. We're running out of time, and I have 4 other mechanisms to give you. These are those mechanisms. HX addition and acid catalyzed hydration. These are similar to each other, but with slight differences. Acid catalyzed hydration has an extra deprotonation step. I'll also have you recognize mechanisms for X2 addition and X2 in water or alcohol, the halohydrin and the haloether addition. These also are very similar to each other, but one of them has an extra deprotonation step. So I do want you to notice that you're basically giving 2 types of mechanisms: carbocation mechanism and halonium ring mechanism. The halonium ring looks like this. Carbocation mechanism, halonium ring mechanism. And within those 2 types, one type will have an extra step. Well, yes, in both of them, it's always the second one has an extra step. So I think rather than trying to show you the mechanism for any of these, do I have the time? Do you want to see it? I think the only one I could get done is X2. Let's say that we have this starting material, propyne, and I take Br2, and I want to show the formation of this stereoisomer. It's 2 steps, which is why I think I might be able to get through it. Step 1 is the halonium ring formation. This is a very cool step. 1 bromine attacks the ring while the ring attacks it, and the other bromine gets kicked off. That's a halonium ring and a bromide. The second step is a backside attack. Sorry, I'm going to make a small change. I wanted some stereochemistry here, so I'm going to show you that this halonium ring is dashed. Since that halonium ring is dashed, and I wanted a stereoisomer where the secondary halide is wedged, I know that my bromide ion does a backside attack at the secondary carbon. A dashed bromine will get replaced with a wedged bromine, backside attack. A dashed bromine gets attacked, bromide attacks the carbon, the CBr bond in the bromonium ring breaks open, and I'm left with that inversion of stereochemistry. Two steps. Easy. When you add solvent, you have to deprotonate after this. We can clarify this more on Thursday, but the last thing I'm going to mention, my bromine attacked at the more substituted carbon on purpose. And my bromide attacked at my more substituted carbon on purpose. The positive charge, the carbon that is able to accept electrons, it's always the more substituted carbon.
Is it due to partial charges?
Partial charges. It's weird to say that there's a partial charge between carbon and carbon, but there is. There's a partial positive on the more substituted. More substituted, more stable with positive. Thank you guys for your time. Try to take a stab at that homework, and if I'm able to, I'll try to give you some feedback even before Thursday. And what you don't understand before Thursday, come back in and we'll finish up our mechanisms on Thursday. We'll do a little nomenclature review. We'll do a little spectroscopy. We'll be ready for our first unit test, all of OCHEM 1 in 3 weeks.
Which reaction did you say that was?
X2 addition, halonium. Have a good night, guys.